Welcome! This video on limits is brought to you by the Learning Center at Vancouver Community College. Visit our website at www.vcc.ca/tlc for more information. We're looking for requests, so please submit your suggestions to mathsciencetutor@vcc.ca. The question is, analyze the asymptotes of a rational function. Asymptotes of a rational function will occur at values of x where the expression cannot be evaluated. This factor in the denominator, and this one, tells us that the function may be undefined at x equals 2 and at x equals -1. The denominator is a third-degree polynomial, a cubic, just like the numerator, so this function has horizontal asymptotes. We'll want to examine the two one-sided limits at 2 and at -1, and both limits to infinity. We'll start with the asymptote at x equals 2. Letting x equal 2 causes no problems for the numerator or the x plus 1 factor in the denominator. The trouble is with the remaining factor. This is the right-hand limit, so we're examining numbers slightly greater than 2. Plugging a number just over 2 into that factor leaves a number just over 0, which we can write as 0 plus. That small positive number gets squared, keeping it positive, and then multiplied by 9, so it's still a small positive number. It's worth learning these two special limits to see what happens with denominators. 65 divided by a small positive number is a large answer. The left-sided limit goes exactly the same way. We can't technically say that this limit exists. The results match, but they're not finite. But the fact that they agree is worth mentioning. Performing the same analysis on the one-sided limits at x equals -1 yields two different answers, which is much more common with a vertical asymptote. This small negative number does not get squared, so the left side limit is a large negative number. Here, the limit definitely doesn't exist. Horizontal asymptotes take a different approach. We've expanded the denominator. As x gets very large, these leading terms leave the others behind in size, and they're in control of the growth of this function. We can get a perspective on their influence by dividing by the largest power of x we see in the problem. When we distribute 1 over x cubed through the problem, we get a lot of fractions with x in their denominators. Those special limits tell us that they all tend to 0, so only the leading terms matter. In almost all cases, the horizontal asymptote at -infinity will yield the same result. That's how limits at asymptotes work. If you'd like more detailed information and some practice problems, look for the Limit Problems worksheet for Math 1100 on our website, vcc.ca/tlc.